In this video, we're going to look at atomic spectra and the arrangement of electrons in an atom. So far, we've learned that the electrons are found outside of the nucleus and sometimes found a long way away from the nucleus, so an atom is largely empty space. But so far, we've not said anything about how the electrons are arranged. And how they're arranged was developed by something called quantum mechanics. And of this, Niels Bohr said the following: everything we call real is made of things that cannot be regarded as real. So when you look at an atom, um, it's very different in reality to how it appears to us. So how it appears to us is called a manifest image. How it is described by quantum mechanics is a scientific image. And there's a big difference between the two. And Niels Bohr goes on to say the following: if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. Because quantum mechanics does not seem to make sense. And for this, we're going to look at the following: explain how data from emission spectra provide evidence for discrete energy levels within the atom. And we're going to look at the Bohr atom, simple treatment of emission spectrum, and the Lyman series and Balmer series. And we're going to look at delta E, which is energy difference between two orbitals, or dE equals hv, where h is Planck's constant and v is frequency, or c over lambda. And we're going to describe the atomic orbitals and look at principal quantum numbers together with s, p, and d orbitals. In this class, we're going to differentiate between shells, orbitals, and suborbitals. And principal quantum numbers refer to shells, and shells can be arranged into different orbitals, which can be s, p, or d, and they have different energy levels, and they also have different shapes. And we're going to look at electronic configurations. But we begin by atomic spectra. And it says this: when atoms are excited by photons, or for that matter, you can just simply heat them up, they emit light of certain wavelengths, which correspond to different colors. The emitted light can be observed as a series of colored lines with dark spaces between them. This series of colored lines is called an atomic spectrum. So this top one is an atomic spectrum. Where the lines are, there is light, and between them we have darkness. Note here we have increasing frequency, and here we have increasing wavelength. And it can be contrasted to visible light, where we have a continuous band of colors, ranging from blue, which is the shortest, to red, which is the longest. And notice wavelength and frequency are inversely related. Frequency basically is related to 1 over the wavelength. So if wavelength is increasing, then frequency is decreasing. So a short wavelength has a very high frequency, and a long wavelength has a low frequency. And the light appears, the emitted light only appears as a series of lines if it is refracted through a prism, just as white light doesn't appear to have different colors unless it's refracted. The same applies to atomic spectra. We only see the light, the different bands of light, if it passes through a prism. And we can see this. We have something, a gas discharging tube containing hydrogen. The hydrogen is put under high temperature and it emits light because it's a high temperature. We put this light through a prism and it separates into different wavelengths and there's darkness between them. So you have violet, which is the shortest, then you have blue, green, and finally red. And as it says, the light produced by a heated gas is separated using a spectrometer. So this basically is a simple spectrometer, and it simply separates light according to the wavelength. And you can look at the YouTube video on it if you wish to. And for hydrogen, the emission spectrum is produced by a series of lines separated by darkness. So we can see a series of lines and there's darkness between them. And this is an emission spectrum. You could also have an absorption spectrum where you have lines of darkness between a continuous color. But we normally see this one here, the emission spectrum, and we can see the lines diverging. That is, becoming further and further apart, so they diverge if wavelength is increasing. If I have a frequency increasing, then the lines would converge. So, with something like a hydrogen atom, in fact, we find different series of lines, all of them, in this case, this is frequency increasing, all of them converging. So I have one series called the Passion, then you have the Burma, then you have the Lyman. There's other series, that's a Bracket and Fund, but we're not really interested in those. The Lyman series is really what we're interested in because it occurs in the visible spectrum. And the pattern of lines, that is the converging lines, has a regularity that can be described mathematically by the Rydberg equation. And there are different series of lines which have different series of lines which belong to different series. That should have said, which belong to different series. But only the Balmer series produces visible light. So the Rydberg equation basically shows how to work out the position of these lines. And we say delta E is equal to minus R over 1 over NF squared minus 1 over NI squared multiplied by a constant Z squared, where delta E is the difference in energy between the final and initial energy level. That's the difference between two energy levels, so the light given off. R is the Rydberg constant, NF is the final energy, Ni is the initial energy, and Z is the atomic number. We don't really have to know the Rydberg equation anymore. But the pattern of distribution of lines was explained by Bohr using the Bohr model of the atom, which says that electrons can only have specific energy values. Electrons travel in fixed circular orbits. So electrons will travel in an orbit, and when they are in an orbit, they will have a specific amount of energy, and this energy remains constant. It doesn't radiate energy, as you'd expect in classical physics. It just has a constant amount of energy when it's in one orbit. And each of these orbits has different energy values, but these energy values are fixed. And this explains when an electron from a high orbit returns to one of a lower energy, it gives off a fixed amount of energy. And all atoms of the same element will give off the same amount of energy when a certain transition occurs. And the production of atomic spectra is explained by Niels Bohr, who made the following postulates. Electrons are found in orbits, and we're calling them orbits right now, not orbitals, with specific amounts of energy, which is fixed. So when it's in one orbit, the energy it has is fixed. And electrons can move from one orbit to another, emitting a fixed amount of energy. So when it returns, it will emit energy, and this energy is given off in the form of light, giving off a photon. So an electron absorbs the exact difference in energy between two levels and makes a quantum leap up. And when an electron makes a quantum leap down, it releases the exact energy difference. And this will always be in the form of a photon. And note there's a large number of different possible orbits, so a large number of different transitions that can occur. And since you have a large number of atoms, some of them will undergo different transitions, and hence you'll get all different wavelengths being produced at the same time, because all transitions will occur, but in different atoms. So the absorption and emission of photons as a result of energy level changes of electrons. If it moves up, electrons are absorbed. If it moves down, electrons are emitted. So each of these transitions causes an emission of light. So the foundation of the modern quantum mechanics was made by Bohr, which the concept of quantized orbitals, which means that restricted, only certain specific energy levels are allowed. Each of these orbits will have a specific amount of energy, and there's no intermediate energy level. It has to go directly from one level to the next one, without ever being in between. And that is why you get a specific amount of energy being given off. You don't get a band of energy, because it's never halfway between one orbit and the next one. The idea of quantum leaps, the concept of electron level transitions or quantum leaps, that show delta E. It actually predicts visible emission spectrum of the hydrogen. So we can work out these energy levels and the differences, and we can it corresponds really to the Rydberg equation, and therefore that's how we know we have these specific energy levels. But the failure of the Bohr model, with more sophisticated equipment, spectral lines were found to consist of closely spaced lines called doublets. So each line really is a doublet, and Bohr model does not accurately predict emission spectra of hydrogen, so of any spectra of any element besides hydrogen. So the Bohr model only works for hydrogen and none others. And there's a fatal flaw. Electrons do not travel in fixed circular orbits. That's wrong. So the foundations of modern quantum mechanics. As it says, the Bohr model, modern quantum accepts quantized energy levels, but rejects Bohr's circular orbits. So we still have these quantized energy levels, and electrons moving from a high energy level to a low one. But it does not, the atom does not look like that. So is it possible to determine the exact trajectory of an electron around the nucleus? And the answer is no, we can't do that. And the reason for that relates to the Heisenberg uncertainty principle, where it says it's impossible to actually determine both the position and momentum of an electron at the same time. You know, for classical physics, where a particle exists, you know its can know its position and momentum at the same time. We can't do this for electrons. And trying to pinpoint the location of a tiny electron requires collision with short wavelength of high-energy photons, which then change the speed and the direction of the electron. And because of that, because the photon, which you need to see the electron, is going to change its position and speed, then by the time you see it, it will be different from how it was when the photon hit it. And therefore, what you see is not how things actually are. And it is better, therefore, to consider an electron as a wave rather than as a particle, whose behavior is described by the Schrödinger equation. We can describe an electron as a wave rather than as a particle. And this can be described by this equation here, which is a wave equation, or the Schrödinger equation. And it's a fairly complex, so we don't really have to know it. But phi squared gives a probability of finding an electron in a given volume. So that's the important part about that. We don't know precisely where an electron is, but we can find the probability of it being in a given volume. And the point is that when we solve the Schrödinger equation, we get three values. N, which is the principal quantum number, that's the shell number. Then you have P, which is the orbital quantum number, because we have different orbitals. And then we have F, which is the magnetic quantum number. And electrons can therefore be placed into shells, subshells, and orbitals. So if you look at this, the first shell really has one subshell, which is S. The second shell has two subshells, an S and 3p orbitals. And the fourth has three subshells, S, well, the third would have the third has sp and d orbitals, and the fourth has sp, d, and f. You can look at those in more data there later. So the orbitals in an atom are arranged into shells, subshells, and orbitals. So we have what they call S, P, and D. Let's see if there's. So the first shell only has an S orbital. The second shell has both S and p. And notice we have 3 p orbitals as well as one s. The third has s, p, and d, but notice the 4s is below the 3d. And the subshells. The first subshell, the S, is shaped like a sphere. The P is dumbbell shaped. The D is a complex dumbbell, or it can be, there's a 1, dz squared, which looks a bit like this. Well, not sorry, it's not given. But there's one D shell which is slightly different. But electrons are now best considered as clouds. So the first shell has an S, which is a cloud. This is also a cloud, so it's no longer a single particle, but it's a cloud occupying a volume. So the planetary model has been abandoned. So the point here is that we know the first shell contains 2 electrons. All of these are in the 1s. The second shell, you have 2 in the s, but then 6 in the p, giving a total of 8. Then in the third shell, we have S, P, and D. 2 in this, 6 in this, and then 10 in this. So you have 2 plus 6 is 8, plus 10 is 18. That's where the third shell can in fact hold 18 electrons. But it behaves as if it's full when it has 8. This aspect here is fairly complex, and you need to go into it in more detail. But that will be for the next class.